Hello, in this lecture we'll answer two questions. The first question, we find out the radius of this small circle. In the second question, we find out the area of this green shape using two different methods. Okay, so we start with the first question. So in the drawing we have a quarter circle. AOB is a quarter circle. We know that line segment OB equals to 16 units in its length. Inside this quarter circle we have a semicircle and this small circle, and our mission is to find out the radius of this small circle or the value of R. Okay, so first of all, we know that AOB is a quarter circle, therefore angle AOB, this angle equals to 90 degrees in its size. In addition, side AO equals to side OB. Both sides are the radii of this quarter circle, therefore they are equal to each other. But we know that side OB equals to 16 units in its length, that is to say, the radius of this quarter circle equals to 16 units, and therefore side AO must be equal to 16 units in its length, because it is also the radius of this quarter circle. So AO equals to 16. The radius of the quarter circle AO equals to 16 units in its length. And in the next step, we'll define the relevant points to this question with letters. We'll define the center of this semicircle. This point is point P. We'll define the center of this small circle. This point is point Q. We define the point of tendency of tangent OB with this circle. This point is point M. We define the touching point of this semicircle with this small circle. This point is point S. And finally, we define the touching point of this big quarter circle with this small circle. This point is point T. AO is the radius of this quarter circle, that equals to 16 units in its length, but AO is also the diameter of this semicircle. So we know that the diameter of this semicircle equals to 16 units in its length, therefore the radius must be equal to half of it. That is to say, the radius must be equal to 16 over 2, that is 8. So the radius AP of this semicircle equals to 8 units in its length, and the radius PO of the semicircle also equals to 8 units in its length. Here we can implement rule 1, because we have the radius QM that is drawn to point M, that is the point of tendency of tangent OB with the small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ, according to rule 1. So if OB is perpendicular to MQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. In the next step, we will do a construction, that is to say, from point Q, that is the center of this small circle, we will draw perpendicular on AO. Again, from point Q, we will draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point Q and AO, this point is point H. By doing this construction, we actually created here quadrilateral HQMO. Inside this quadrilateral HQMO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HQMO, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral HQMO as a rectangle because it has 4 right angles. So I write it down. Quadrilateral HQOM is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle HQMO, side QM must be equal to the opposite side HO. But QM is R, according to what is given in the equation, therefore HO must be equal to R. R is the radius of this small circle, the radius that we are looking for in this question. In this moment, we have an external notch between the semicircle and the small circle. That is to say, the semicircle touches this small circle at this point, externally at this point, point S. Point S is the touching point of this semicircle with this small circle. Therefore, we can implement here rule 10. I'll repeat quickly on rule 10. According to rule 10, if 2 circles touch each other externally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have 2 circles. The center of this circle is here at point O, the center of this circle is here at point M. And the straight line that connects their centers together is of course the straight line OM, and according to rule 10, this rule 10, the straight line that connects the centers together, that is to say this straight line OM, must pass through their touching point, that is point P. Or OPM is one straight line. According to rule 10, OPM is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have this semicircle touches externally this small circle at point S. So we have here an external notch between those 2 circles. The center of this semicircle is here at point P. The center of this small circle is here at point Q. And the straight line that connects their centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point S. Again, the straight line PQ must pass through point S, that is their touching point. Or PSQ is one straight line. Again, PSQ is one straight line. So we connect points P and Q together by a straight line. And the straight line PQ must pass through point S. So you can see here that the straight line PQ passes through point S, or PSQ is one straight line. Again, PSQ is one straight line. And what is exactly the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and then at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle that is equal to 8 units. What is the definition of line segment QS? Line segment QS starts from point Q, that is the center of this small circle, and ends at point S, that is the point in the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle that is equal to R. R is the radius that we are looking for in this question. According to rule 10, we should find out that PSQ is one straight line, and therefore PQ is a straight line, and PQ must be equal to PS plus SQ. Again, according to rule 10, PQ, the straight line PQ, must be equal to PS plus SQ. So I write it down. PQ must be equal to PS plus SQ. So PQ equals to PS. PS is 8 plus SQ. SQ is R. So in total, PQ equals to S plus R. PQ equals to 8 plus R. Okay, PQ equals to 8 plus R. What is the length of line segment PH? From the drawing, it is very easy to see that PH equals to PO minus HO. Again, PO minus HO equals to PH. So write it down. PH equals to PO minus HO. So PH equals to PO. PO is 8, it is the radius of the semicircle, that is equal to 8 units in its length, minus HO. We only found out that HO equals to R. So in total, we actually found out that PH equals to 8 minus R. PH, this line segment PH equals to 8 minus R. And PQ in total equals to 8 plus R. In the next step, I'll copy the right triangle PHQ in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle PHQ. Repeat again, we'll implement the Pythagoras theorem on the right green triangle, triangle PHQ. Here by PT is a abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle PHQ that I copied from the original drawing. This right triangle PHQ, PQ squared, that is the square of the hypotenuse, must be equal to PH squared plus HQ squared. So I write it down. According to the Pythagoras theorem, in this right triangle PHQ, PQ squared must be equal to PH squared plus HQ squared. The hypotenuse PQ equals to 8 plus r, therefore PQ squared is 8 plus r squared, and it is equals to pH squared. pH is 8 minus r, therefore pH squared is 8 minus r squared plus HQ squared. HQ is the missing side, so we leave it as it is. So actually found out that according to the Pythagoras theorem, 8 plus r squared equals to 8 minus r squared plus HQ squared. We will open the brackets on both sides of this equation, and we get that 8 plus r squared equals to 8 squared, that is 64, plus r squared plus 2 times 8 is 16 times r. So it is plus 16r, and it is equals, in the other side of the equation we have here 8 minus r squared. 8 minus r squared equals to 8 squared, that is 64, plus r squared minus 2 times 8 is minus 16 times r. We have here plus HQ squared. So here we have 64 on both sides of this equation, so 64 will get cancelled. And we have here r squared on both sides of this equation, so r squared also will get cancelled. After cancelling those two expressions, we left in this side of the equation with 16r. The other side of this equation we have minus 16r plus HQ squared. 16r equals to minus 16r plus HQ squared. Here we add 16r to this equation, and we get that 16r plus 16r is 32r. 32r equals to HQ squared. So here we take a root out of this equation, and we get that HQ equals to, actually 32r, 32 is 16 times 2, so actually HQ squared equals to, we substitute 32 by 16 times 2, so HQ squared equals to 16 times 2 times r. Now we take a root out of this equation, and we get that the missing side HQ equals to the square root of 16, that is 4, and inside the root we left only with 2r. So she found out that HQ, the missing side HQ, equals to 4 times the square root of 2r. So here, this is side HQ, and it is equals to 4 times square root of 2r. But we have already found out that HQMO is a rectangle, and we know that the opposite sides of rectangle HQMO must be equal to each other. So a rectangle HQMO, side HQ must be equal to the opposite side OM. But HQ equals to 4 times square root of 2r, therefore OM must be also equal to 4 times square root of 2r. In the drawing, we have an internal notch between the big quarter circle and this small circle. That is to say, they are touching each other internally at point T. Repeat again, the big quarter circle touches the small circle at this point, point T, internally. And whenever you have an internal notch between two circles, you can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles, and the center of the big circle is here at point O. The center of this small circle is here at point M. And their touching point is here at point P. And according to this rule 9, the straight line that connects their centers together is of course the straight line OM. So according to rule 9, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, according to rule 9, OMP is one straight line. Okay, we can actually implement rule 9 in our drawing. Well, because in our drawing, the small circle touches the big quarter circle at this point, point T. So we have here an internal notch between those two circles. We know that the center of the big quarter circle is here at point O. The center of this small circle is here at point Q. And the straight line that connects their centers together is the straight line OQ. And according to rule 9, the straight line OQ must pass through point T, that is their touching point. Or OQT is one straight line. According to rule 9, OQT is one straight line. So I connect between points O and Q, and according to rule 9, the straight line OQ passes through point T, or OQT is one straight line. Okay. Repeat again, OQT is one straight line. If OQT is one straight line, it means that OT is a straight line. OT is a straight line, but what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and ends at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of the quarter circle, that is equal to 16 units according to what is given as the question. So write it down, OT equals to 16 units in its length. It is the radius of the quarter circle. And what is the definition of line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and ends at point T, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. R is the radius that we are looking for in this question. And we have already found out that OQT is one straight line according to rule 9. And therefore, OT, or OQ, this line segment OQ, must be equal to OT minus QT. Because of the fact that OQT is one straight line, it means that OQ equals to OT minus QT. So write it down. OQ equals to OT minus QT. So OQ, this line segment OQ equals to OT. OT is 16. Minus QT. QT is R. So in total, OQ equals to 16 minus R. OQ equals to 16 minus R. So I write it down. OQ equals to 16 minus R units in its length. In the next step, I'll copy the right blue lower triangle OQM in a new page, and we'll implement the Pythagoras theorem on this right blue triangle, triangle OQM. Here by PT is the evaluation for Pythagoras theorem. The hypotenuse QO equals to 16 minus R. QM equals to R, it is the radius that we are looking for in this question. And finally, we already found out that side OM equals to 4 times square root of 2R. this is the right blue triangle OQM that I got from the original drawing. According to the Pythagoras theorem, in this right triangle OQM, QO square equals to QM square plus MO square. Again, QO square equals to QM square plus OM square. So I write it down. QO square, that is the square of the hypotenuse, equals to OM square plus QM square. QO is 16 minus R, therefore QO square is 16 minus R square, and it is equal to OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square plus QM square. QM is R, therefore QM square is R square. So if we're going according to the Pythagoras theorem, we found out that 16 minus R square equals to 4 times square root of 2R square plus R square. Here we'll open the brackets on both sides of this equation, and we get that 16 minus R square equals to 16 square, that is 256, plus R square, minus 2 times 16 is minus 32 times R, so it is minus 32R, and it is equal to 4 times square root of 2R square. 4 times square root of 2R square equals to 4 square, that is 16, and square root of 2R square equals to 2R, because the power cancels the root and we have to only with 2R plus R square. So she found out that 256 plus R square minus 32R equals to 16 times 2R is 32R plus 32R plus R square. Here we have R square on both sides of this equation, so R square gets cancelled. After cancelled R square, in this side of the equation we have to only 256 minus 32R, and it is equal to 32R. Here we add 32R to this equation, and we get that 256 equals to 32R plus 32R is 64R. 256 equals to 64R. Here we divide this equation by 64, and finally we get that R equals to 256 over 64 is 4. R equals to 4 units in its length. Actually, we found out that the radius of this small circle R equals to 4 units in its length. So we finished with the first question. In the next step, I will present to the second question, and we solve the second question in 2 different methods. Our mission in the second question is to find out the area of this green shape. So in the drawing we have a quarter circle. AOB is a quarter circle. We know that side OB equals to 2 units in its length. We also know that AD equals to DO. I repeat again, our mission is to find out the area of this green shape. We know that this angle DCB equals to 90 degrees in its size. Therefore, the green shape, it is actually the right triangle, the right green triangle DCB. So our mission actually is to find out the area of this green right triangle DCB. So we start with the first method. We know that AOB is a quarter circle, therefore angle AOB must be equal to 90 degrees in its size. and also side AO must be equal to side OB. They are both the radii of this quarter circle, therefore they are equal to each other. But the radius OB equals to 2, therefore the radius AO must be equal to 2. AO equals to 2 units in its length. It is given us the equation that AD equals to DO. So if we define the length of line segment AD as x, then DO must be also equal to x because they are equal to each other according to what is given as the question. AD is x, DO is x. So AD plus DO, it is actually x plus x. X plus x equals to AO, that is 2. Repeat again, x plus x equals to AO, that is 2. So x plus x equals to 2, x plus x is 2x, so 2x equals to 2. We divide this equation by 2 and get that x equals to 2 over 2, that is 1. So AD is equal to x equals to 1. And DO, that is also equals to x, equals to 1 unit in its length. In the next step, I'll copy this right triangle DOB in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle DOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the version for Pythagoras theorem. So actually, this is the right triangle DOB that according to the original drawing, according to the Pythagoras theorem, in this right triangle DOB, DB square equals to DO square plus OB square. Again, DB square equals to DO square plus OB square. So write it down. DB square, that is the square of the hypotenuse, equals to DO square plus OB square. The hypotenuse DB is the missing side, so we leave the CT. So DB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So in total, DB square equals to 1 plus 4, that is 5. DB square equals to 5. We take out all of this equation and finally get that DB equals to the square root of 5 units in its length. So actually, this is side DB that is equal to square root of 5 units in its length. In the next step, we'll complete this quarter circle to a circle. So completed the quarter circle to a circle, and we'll extend the radius BO by straight line until it touches the circle. We define the touching point of the extended radius BO with this circle, this point, as point P. The radius BO, it is absolutely a straight line. Again, the radius BO, it is absolutely a straight line. And we extended the straight line BO by straight line, and the result is BP. When we extend the straight line by straight line, the result must be a straight line, therefore BP is a straight line. BP is a straight line that touches the circle at 2 points, B and P, therefore BP is a chord, because it is a straight line that touches the circle at 2 points, and then straight line that touches the circle at 2 points, it is defined as a chord. So BP is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. So write it down. We can find out that BP is the diameter of the circle. So we know that BP is a straight line. So if we focus on the upper side of the straight line BP at point O, here the sum of the angles must be equal to 180 degrees according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. What is the definition of line segment OP? Line segment OP starts from point O, that is the center of the circle, and that's at point P, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of the circle, that is equal to 2 units in its length, because the radius of the quarter circle equals to 2. Okay. In the next step, we will extend side CD by straight line until it touches the circle. Repeat again, we extend this side CD by straight line until it touches the circle. The question is where the extended side CD will touch the circle. We will assume that the extended side CD will touch the circle at this point, not at point P, but in any other point. This point, we define the touching point as point G. Repeat again. We shall find out that after we extend side CD, it will touch the circle at this point G. Okay, so by doing this construction, we created peripheral angle BCG. This is the peripheral angle BCG that we created, but peripheral angle BCG equals to 90 degrees in its size according to what is given as the question. Angle BCG equals to 90 degrees. And so we have peripheral angle BCG, that is a right angle, and is subtended on BG. Again, peripheral angle BCG, that is equal to 90 degrees in its size, is subtended on chord BG. Okay, and chord BG is definitely not the diameter of the circle. Why chord BG is not the diameter of the circle? Because from point B you can have only one diameter. We have already found out that from point B we have the diameter BP. So any other chord from point B will not be the diameter of the circle, therefore BG is not the diameter of the circle. So we found out that peripheral angle BCG, that is a right angle, is not subtended on the diameter of the circle, because it's subtended on BG, that is not the diameter of the circle, and this is a contradiction to rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. We have peripheral angle MAN. This is peripheral angle MAN that is equal to 90 degrees in its size, and it's subtended on MN, that is the diameter of the circle. And therefore, according to rule 5, peripheral angle BCG must be subtended on BP, that is the diameter of the circle, and not on BG. BG is not the diameter of the circle, so we have contradiction to rule 5, because peripheral angle BCG is not subtended on BP, that is the diameter of the circle. In order to avoid the contradiction to rule 5, we conclude that our assumption that the extended side CD will touch the circle at point G is not correct, and therefore we must conclude that the extended side CD will touch the circle at point P and not in any other point. Otherwise, we have contradiction to rule 5. Okay, so the extended side CD must touch the circle at point P and only at point P. Now we have peripheral angle BCP that is equal to 90 degrees in its size. Anyway, when extend side CD, you will never change the size of this angle, that is right angle. Okay? So we have peripheral angle BCP that is a right angle, it is equal to 90 degrees. And this peripheral angle BCP that is equal to 90 degrees is subtended on PB, that is the diameter of the circle. Now we don't have any more contradiction to rule 5. Okay? So in the next step, I'll copy the right triangle DOP in a new page, and we implement the Pythagoras theorem on this right triangle DOP. So actually, this is the right triangle DOP that is according to the original drawing, according to the Pythagoras theorem. This right triangle DOP, dP square equals to dO square plus PO square. So dP square equals to dO square. dO is 1, therefore dO square is 1 square, that is 1, plus PO square. PO is 2, therefore PO square is 2 square, that is 4. So in total, PO square equals to 5. We take out of this equation, we found out that PO equals to the square root of 5 units in its length. So this is side PO, Actually, it is side PD. Here, dp squared equals to 5. We take out of this equation, we get that dp equals to square root of 5 units in its length. dp equals to the square root of 5 units in its length. In the next step, we'll extend the radius AO by a straight line until it touches the circle. And we'll define the touching point of the extended radius AO with this circle. This point is point Q. So what is the definition of line segment OQ? Line segment OQ starts from the center of the circle, that is to say from point O, and then ends at point Q, that is the point on the circle itself. So this is exactly the definition of a radius. Therefore OQ is the radius of this circle that is equal to 2 units in its length. So here we can implement rule 11. I'll repeat quickly on rule 11. Rule 11 is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, point O is the intersection point, point O is the intersection point of those two chords, then the following equation will be true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, we can implement rule 11 in our drawing. Why? Because in our drawing we have chord AQ, this is chord AQ, that intersects with chord CP, this is chord CP at point D. So write it down. Now drawing, chord AQ intersects with chord CP at point D. Repeat again, in our original domain, chord AQ intersects with chord CP at point D. Therefore, according to rule 11, the following equation will be true, that AD times DQ equals to CD times DP. And again, according to rule 11, we get that the following equation is true, that AD times DQ equals to CD times DP. Okay, so AD equals to 1 times DQ. DQ in total equals to 1 plus 2, that is 3. Again, DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times DP. DP equals to the square root of 5 units. So total, according to rule 11, we found out that 1 times 3 equals to CD times square root of 5. So 1 times 3 is 3, so 3 equals to CD times square root of 5. Here we divide this equation by square root of 5. And we get that CD, the missing side CD, equals to 3 over square root of 5 units in its length. So here, this is side CD, and it is equals to 3 over square root of 5 units in its length, so I write it down. Our mission is to find out the area of this green shape, so I copy the right green triangle DCB in a new page, and we will implement the Pythagoras theorem on this right triangle DCB in order to find out the missing side CB. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle DCB that according to the original drawing. According to the Pythagoras theorem, in this right triangle DCB, the square of the hypotenuse is DB, the square of the hypotenuse is DB square, and it must be equal to DC square plus CB square. The hypotenuse dB equals to the square root of 5, therefore dB square is square root of 5, that is 5, and it is equals to dC square. dC equals to 3 over square root of 5, therefore dC square equals to 3 over square root of 5 square minus CB square. CB is the missing side, so we leave this it is. So we found out that according to the Pythagoras theorem in the right triangle DCB, 5 equals to 3 over square root of 5 square equals to 3 squared, that is 9, over square root of 5 squared, that is 5, minus CB square. Here we subtract 9/5 from this equation, and we get that 5 minus 9/5 equals to CB square. Here we multiply 5 by 5 and then we divide it by 5 in order to account factor with 9 over 5. So 5 times 5 is 25, so in total in the numerator of this expression we have 25 minus 9 divided by 5 equals to CB square. 25 minus 9 is 16, so in total this expression equals to 16 over 5. So 16 over 5 equals to CB square. Here we take a root out of this equation, and finally we get that the missing side CB is equals to the square root of 16, that is 4 over square root of 5. So we actually found out that the missing side CB equals to 4 over square root of 5 units in its length. This is the missing side CB, that is equal to 4 over square root of 5 units. I repeat again that our mission is to find out the area of this green shape. So the area of the green shape is actually equals to the area of this green right triangle DCB. So what is the area of the green right triangle DCB? The area of any triangle is equals to the base of the triangle times the height to the base over 2. We choose the base of this green right triangle DCB as DC. The base is DC, and the height must be CB because CB creates 90 degrees with the height DC. This angle equals to 90 degrees. So the height is CB. To repeat again, the base of the right triangle DCB is DC, the height is CB over 2. DC equals to 3 over square root of 5 units times CB. CB equals to 4 over square root of 5 units divided by 2. So the area of the green shape equals to the middle of this expression. Here 3 times 4 is 12 over square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 is 12 over 5 times 2, so it is 12, and 5 times 2 is 10. It is 12 over 10. Here we divide both the numerator and the denominator of this number by 2. 12 over 2 is 6, and 10 over 2 is 5. So conclusion, actually found out that the area of this green shape equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. Repeat again. The area of this green shape equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. We finished with the first method. In the next step, I present to you how to find out the area of this green shape according to the second method. Means again that our mission is to find out the area of this green shape. So we know that AOB is a quarter circle, therefore angle AOB equals to 90 degrees in its size. Actually, we have already found out in the first method that AD equals, we know that AD equals to DO, and we already found out that AD equals to 1 unit in its length. DO also equals to 1 unit in its length. OB is the radius of the quarter circle, that is equal to 2, and AO is also the radius of the quarter circle, that is equal to 2 units in its length. Okay? So in the next step, we complete this quarter circle to a circle. We'll extend the radius BO by straight line until it touches the circle. define the tension point of the extended radius PO if this circle, this point is point P. PO is the radius of the quarter circle that is equal to 2 incidence length. I want to explain in the first method that PB is a straight line, and according to the rule that the sum of the angles on the upper side of the straight line at point O must be equal to 180 degrees, the missing angle here must be equal to 90 degrees in its size. In the next step, we'll extend side CD by straight line until it touches the circle. I've already proved that when you extend side CD by straight line, the only point that it can touch the circle is point P and not in any other point. Otherwise, we get contradiction to Rule 5. In order to avoid contradiction to Rule 5, the extended side CD must touch the circle at point P and point P only, and not in any other point. Here, actually, I can implement the Pythagoras theorem on this right triangle PDO. Actually, we already found out in the first method that when you have a right triangle with sides 2 and 1, then the hypotenuse must be equal to the square root of 5 units. Now we define and focus on the right triangle DOP. We define angle DPO as theta. So in the right triangle DPO, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big right triangle PCB, in the big right triangle PCB, this angle equals to theta, this angle equals to 90 degrees, therefore the missing side, the missing angle here must be equal to 90 degrees minus theta. In the next step, we'll prove that the right big triangle PCB is similar to the right small triangle PDO. So I write it down. We'll prove that the right big triangle PCB is similar to the small right triangle PDO. So why the right big triangle PCB is similar to the right small triangle PDO? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is the angle PCB, the right big triangle PCB, and it is equal to this angle, it is actually angle DOP in the right small triangle PDO. Repeat again. Angle PCB, the right big triangle PCB equals to angle POD in the right small triangle PDO. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to angle theta as it is belongs to the big triangle PCB, it will be defined as angle BPC, and it equals to itself. So if you relate to angle theta as it belongs to the right small right triangle DPO, it will be defined as angle DPO. So really, this equation means that angle theta equals to itself. We just call to angle theta two different names. So angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is angle CBP. In the right big triangle PCB, and it is equals to this angle, that is actually angle PDO. In the right small right triangle PDO. Repeat again. Angle CBP in the right big triangle PCB equals to angle PDO in the right small triangle PDO. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all the triangles inside the right big triangle PCB are correspondingly equal to all the triangles inside the right small triangle PDO, and therefore the big triangle PCB is similar to the small triangle PDO according to angle similarity rule. So I write it down. The big triangle PCB is similar. This is the sign of similar to the right small triangle PDO according to angle similarity rule. And from the fact that the right big triangle PCB is similar to the right small triangle PDO, we will derive that the following relationship exists between their sides. We derive that side PD in the small right triangle PDO over side PB in the big right triangle PCB equals to side DO in the small right triangle PDO over side CB in the right big triangle PCB, and it is also equals to side PO in the small right triangle PDO over side CP in the big right triangle PCB. And again, we derive that PD over PB equals to DO over CB equals to PO over CP. PD equals to the square root of 5 over PB. PB is the diameter of the circle, that is equals to 2 plus 2, that is 4. So PB is 4, and it is equals to DO. DO is 1. DO is 1. Over CB. CB is the missing side, so we leave it as it is. and it is equals to PO. PO equals to 2 over CP. CP in total equals to CD plus square root of 5. Again, CP in total equals to CD plus square root of 5. So in conclusion, according to equation 1, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over CD plus square root of 5. Those two expressions are equal to each other, therefore we create equation 1 from those two expressions that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation 1, and we get that square root of 5 times CB equals to 4. Here we divide this equation 1 by square root of 5. When we get that according to this equation 1, CB equals to 4 over square root of 5 units. This is side CB. This is equals to 4 over square root of 5 units in its length. Already known. We will continue to focus on the log equation 1. This log equation 1. Those two expressions, they are equal to each other. Therefore, we get equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that square root of 5 over 4 equals to 2 over CD plus square root of 5. Okay, again, according to equation 2, we should find out that square root of 5 over 4 equals to 2 over CD plus square root of 5. Here we cross multiply this equation 2, and we get that square root of 5 times CD plus square root of 5 equals to 4 times 2, that is 8. So in conclusion, we found out that according to equation 2, square root of 5 times CD plus square root of 5 equals to 8. Here we open the brackets on this side of this equation 2, and we get that according to this equation 2, square root of 5 times CD equals to plus square root of 5 plus square root of 5. Square root of 5 times square root of 5 is 5, so it is square root of 5 times CD plus 5 equals to 8. Here we subtract 5 from this equation 2 and get, according to this equation 2, in this side of equation 2 we have square root of 5 times CD, and it is equals to 8 minus 5 is 3. So here we divide this equation 2 by square root of 5, and you get that according to this equation 2, CD equals to 3 over square root of 5 units in its length. So actually, this is side CD, that is equals to 3 over square root of 5 units in its length. Our mission is to find out the area of this green shape. I repeat again that the green shape, it is actually the right green triangle DCB. Therefore, the area of the green shape is actually equals to the area of the right green triangle DCB. And the area of green triangle equals to the base of the triangle times the height over 2. because again the area of the green shape equals to the area of the right triangle, triangle DCB, and the area of any triangle equals to the base of the triangle times the height to the base over 2. So repeat again what we already done in the first method. The base, we choose the base of this right triangle DCB is DC. The height is CB because we get 90 degrees with the base. The height is CB over 2. Again, the base is DC, the height is CB over 2. DC equals to 3 over square root of 5 times CB equals to 4 over square root of 5 divided by 2. So the area of the green shape equals to the value of this expression. The value of this expression is equals to 3 times 4 is 12 over square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 is 12 over 5 times 2, so it is 12, and 5 times 2 is 10, so it is 12 times 10. Here we divide both the numerator and the denominator of this number 12 over 2 by 2. 12 over 2 is 6, and 10 over 2 is 5. So the area of the green shape equals in total either to 6/5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, so we finished with the second method. In the next step, I'll summarize the lecture. We'll start with the first question, of course. So, in the first question, our mission is to find out the radius of this small circle. So, in the drawing, we have a quarter circle. AOB is a quarter circle. Inside this quarter circle, we have this semicircle and the small circle. Repeat again, our mission is to find out the radius of this small circle or the value of R. Okay. So first of all, we know that AOB is a quarter circle, therefore this angle AOB equals to 90 degrees in size. And AO and OB, they are both the radii of the quarter circle, therefore they are equal to each other. But the radius OB equals to 2, therefore the radius AO must be also, again, we know that the radius OB equals to 16 units in its length. And therefore the radius AO must be also equal to 16 units in its length. But the radius AO that is equal to 16, it is also the diameter of the semicircle. So we know that the diameter of this semicircle equals to 16, therefore the radius must be equal to half of it. So the radius AP of the semicircle equals to 8, and PO also equals to 8. So here we can implement rule 1. The radius QM is going to point M, that is the point of tendency of tangent OB in this small circle. Whenever we have a radius that is going to the point of tendency, then tangent OB will be perpendicular to the radius MO. If OB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did a construction, that is to say from point Q, that is the center of the small circle, this small circle, we do perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. By doing this construction, created quadrilateral QH OM. Inside quadrilateral QH OM, we have 1, 2 3 articles. The sum of 3 articles is 270 degrees. So So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the areas in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. For inside quadrilateral QHOM, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a right angle plus a square. So we relate to this quadrilateral QHOM as a right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So right angle QHOM, side QM must be equal to the opposite side or edge O. QM must be equal to edge O, but QM equals to R according to ordered equivalence equation. Therefore, edge O must be also equal to R. So, in the domain we have an external arch between the semicircle and this small circle. That is to say, they are touching each other internally at point S. And according to rule 9, whenever you have an external arch between two circles, then the straight line that connects their centers together must pass through their touching point. The straight line of this semicircle is at point P. The straight line of this circle is at point Q. And the straight line that connects the centers together, it is actually the straight line PQ. And according to rule 10, actually the straight line PQ must pass through point S, that is their touching point. Or PSQ is one straight line. Again, PSQ is one straight line. But what is the definition of the straight line PS? The straight line PS starts from point P, that is the center of the semicircle, and that's at point S, that is the point of the semicircle itself. Therefore, PS is the radius of the semicircle, that is equal to 8. According to what we have already found out. What is the definition of line segment QS? Line segment QS starts from point Q, that is the center of the small circle, and that's at point S, that is the point of the small circle itself. So therefore QS is the radius of the small circle, that is equal to R. So PSQ is one straight line, therefore PQ must be also a straight line. This is according to rule 10. So PQ is a straight line. And what is the length of the straight line PQ? PQ must be equal to PS plus SQ. Because of the fact that according to rule 10, PSQ is one straight line, it means that PQ in total will be equal to PS plus SQ. Okay, here we have PQ equals to PS plus SQ. PS is 8, PQ is R, therefore in total PQ equals to 8 plus R. Okay, PQ equals to 8 plus R. So here we have, so the aperture of the green triangle PQ is 8 plus R. What is the length of this line segment PH? From the drawing it is very easy to see that PH equals to PQ minus edge O. Okay, PH equals to PQ minus edge O. Here PH equals to PO minus edge O. So PH equals to PO, that is 8, minus edge O, that is R. So in total, PH equals to 8 minus R. In the next step, I copied the right green triangle PHQ in a new page and implemented the Pythagoras theorem of this right green triangle, triangle PHQ. This is the right triangle PHQ that I copied from the original drawing. So according to the Pythagoras theorem of this right triangle PHQ, PQ square equals to PH square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. Here we open the brackets on both sides of this equation and found out that actually that 8 plus R square equals to 8 squared, that is 64, plus R square plus 2 times 8, that is 16 times R. And the other side of this equation we have 8 minus R square. 8 minus R square equals to 8 squared, that is 64, plus R square minus 2 times 8 is minus 16, so it is minus 16R plus HQ square. Here we have 64 on both sides of this equation, so 64 will get cancelled, and we have R square on both sides of this equation, so R square also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 16R. In the other side of this equation we left with minus 16R plus HQ square. So we found out actually that 16r equals to minus 16r plus HQ squared. Here we added 16r to this equation and finally found out that 16r plus 16r is 32r, so 32r equals to HQ squared. 32 is 16 times 2, so 732 by 16 times 2. We found out actually that HQ square equals to 32 is 16 times 2 and times r. So HQ square equals to 16 times 2 times r. We took out of this equation and found out that HQ equals to the square root of 16 is 4. So inside the root we have only 2r. So actually, in found out that HQ equals to 4 times square root of 2r. So this is side HQ, that is equals to 4 times square root of 2r. But we know that we already found out that HQMO is a rectangle, and we know that the opposite sides of rectangle are equal to each other. So rectangle HQMO, side HQ must be equal to the opposite side DM. But HQ equals to 4 times square root of 2r, therefore OM must be also equal to 4 times square root of 2r. HQ equals to OM. HQ equals to 4 times square root of 2r, therefore OM must be also equal to 4 times square root of 2r. So in the drawing we have an internal margin between this small circle and the big quarter circle. That is to say, they are touching each other internally at point T. Therefore, we can implement a rule 9. According to rule 9, the straight line that connects the centers of the two circles that have an internal margin between them must pass through their touching point. Their touching point is here at point T. The center of the big quarter circle is here at point O. The center of the small circle is here at point Q. The straight line that connects their centers together is the straight line OQ. And according to rule 9, the straight line OQ must pass through their touching point, that is point T. Or OQT is one straight line. Again, OQT is one straight line according to rule 9. So we connected point O and Q together by straight line, and according to rule 9, it must pass for point T, that is to say OQT is one straight line. So if OQT is one straight line, it means that OT is also a straight line. So, but what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and then at point T, that is a point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of the quarter circle, that is equals to 16 units in its length. Here, OT equals to 16. And what is the definition of line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and then at point T, that is a point on this small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. So in total, OQ must be equal to OT minus QT. Because of the fact that OQT is one straight line, it means that OQ must be equal to OT minus QT. Again, here, OQ must be equal to OT minus QT. Again, OQ must be equal to OT minus QT. Because OQT is one straight line according to rule 9. So OQ equals to OT, that is 16, minus QT, that is R. So in total, OQ equals to 16 minus R. We know that QM equals to R according to what is given as a question, and we already found out that OM equals to 4 times square root of 2R. In the next step, I copied this right blue triangle OQM in a new page, and we implemented the Pythagoras theorem on this right blue triangle OQM. This is the right blue triangle OQM that I copied from the original domain. According to the Pythagoras theorem, in this right triangle OQM, OQ square equals to QM square plus OM square. Again, OQ square equals to OM square plus MQ square. OQ is 16 minus R, therefore OQ square is 16 minus R square. And it must be equal to OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square plus QM square. QM is R, therefore QM square is R square. So in conclusion, I can find out that 16 minus R square equals to 4 times square root of 2R square plus R square. Here we open the brackets on both sides of this equation and finally found out that 16 minus R square equals to 16 squared, that is 256 56 plus r squared minus 2 times 16, that is minus 42 times r. And it is equal to 4 times square root of 2r squared. 4 times square root of 4 times square root of 2r squared equals to 4 squared, that is 16. And here the power cancels the root, we left only with 2r. So in total this expression equals to 16 times 2r plus r squared. So 256 plus r squared equals to 256 plus r squared minus 32 equals to 16 times 2r is 32r plus r squared. Here we have r squared on both sides of the equation, so r squared will get cancelled. After cancelling r squared, in this side of the equation we left only with 256 minus 32r. In the other side of the equation we left only with 32r. So 256 minus 32r equals to 32r. Here we add 32r to this equation, and I found out that 256 equals to 32r plus 32r, that is 64r. 256 equals to 64r, here we divided this equation by 64, and finally found out that r equals to 256 over 64. 256 over 64 is r. And 256 over 64 is 4. So we found out that the radius of this small circle r equals to 4 units in its length. So we finished with the first method. In the next step, I presented to you how to find out the radius of this small circle. Actually, we finished with the first question, and then I presented to you the second question, and we solved the second question in two different methods. Our mission in the second question is to find out the area of this green shape. So in the drawing we have a quarter circle, A or B is a quarter circle. The radius of this quarter circle is roughly OB equals to 2. In addition, we know that AD equals to DO, and this is again DCB, that is the right angle. Again, our mission is to find out the area of this green shape. The green shape is actually the right green triangle DCB. So our mission is to find out the area of the green right triangle DCB. So in the first method, we know that AOB is a quarter circle, therefore angle AOB must be equal to 90 degrees in its size. In addition, side AO must be equal to side OB, they are both the radii of the circle, therefore they are equal to each other. But the radius OB equals to 2, therefore the radius AO must be equal to 2. We know that AD equals to DO, so if we define AD as x, then DO must be also equal to x. So x plus x is AD plus DO, that is AO. AO is 2, so x plus x equals to 2. X plus x is 2x, so 2x equals to 2, therefore x equals to 1. AD that is equal to x equals to 1, and DO that is also equals to x equals to 1. In the next step, I copied the right triangle DOB in a new page and implemented the Pythagoras theorem on this right triangle, triangle DOB. This is the right triangle, triangle DOB that I copied from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. The hypotenuse in this right triangle DOB is dB, therefore the square of the hypotenuse is dB square, and it must be equal to DO square plus OB square. dB is the missing side, so we leave it as it is, so dB square equals to DO square. DO is 1, therefore DO square is 1 square, that is 1, plus OB square. OB is 2, therefore OB square is 2 square, that is 4. So in total we can find out that dB square equals to 1 plus 4, that is 5. dB square equals to 5, we took a root out of this equation, and finally found out that dB equals to the square root of 5 units in its length. This is side dB, that is equal to the square root of 5 units in its length. In the next step, we did the construction, that is to say, we completed this quarter circle to a circle, and we extended the radius BO by side line until it touches the circle at this point. We defined the touching point of the extended radius BO with this circle, this point, as point P. So BO is a radius, it is absolutely a straight line. We extended the side line BO by side line, therefore the result must be a straight line. Therefore, the result B is BP. Therefore, BP must be a straight line. So if you focus on the upper side of the straight line BP at point O, here the sum of the areas must be equal to 180 degrees according to rule 3, that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of BP at point O? We have this angle that is the right angle, plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. What is the definition of line segment OP? Line segment OP starts from point O, that is the center of the circle, and ends at point B, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, OP is the radius of this OP is the radius of this circle, that's equal to 2. We already found out that BP is a straight line, but BP is a straight line that touches the circle at 2 points B and P. Therefore, BP is a chord. BP is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. Here, BP is the diameter of the circle. In the next step, we extended side CD by a straight line until it touches the circle. The question is where the extended side CD will touch the circle. We will assume that the extended side CD will touch the circle at point G and not at point P. Okay? The extended side CD will touch the circle at point G. Therefore, we will have a peripheral angle BCG that is equal to 90 degrees in its size according to what is given as the question. And this peripheral angle BCG is subtended on BG, that is definitely not the diameter of the circle. Why? Because from point B we can have only one diameter. And the only one diameter that you can draw from point B is the diameter of BP. Therefore, BG is definitely not the diameter of the circle. Therefore, we have a contradiction to rule 5. Why? Because according to rule 5, any peripheral angle that's equal to 90 degrees in its size must be subtended on the diameter of the circle. But we have a peripheral angle BCG that is equal to 90 degrees in its size and still is not subtended on the diameter of the circle, that is BP, because it's subtended on BG. So we have contradiction to rule 5. And in order to avoid contradiction to rule 5, we must assume that the extended side CD will touch a circle at point P and not in any other point. And then we will not have any more contradiction to rule 5. Well, because we have a peripheral angle BCP that equals to 90 degrees in its size, and it's subtended on BP, that is the diameter of the circle, exactly according to rule 5. In the next step, I copied the right triangle ODP in a new page and we implemented the Pythagoras theorem on this right triangle ODP. Actually, this is the right triangle ODP that I copied from the original domain according to the Pythagoras theorem, and this right triangle ODP, PD squared equals to DO squared plus PO squared. So PD squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1. Plus PO squared. PO is 2, therefore PO squared is 2 squared, that is 2. So in total, PD squared equals to 1 plus 4, that is 5. So PD squared equals to 5. We took out all those equations and finally found out that the opposite PD equals to the square root of 5 units in its length. Here, PD or DP equals to the square root of 5 units in its length. In the next step, we extended the radius AO by straight line until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. What is the definition of line segment OQ? Line segment OQ starts from point O, that is the center of the circle, and that's at point Q, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OQ is the radius of this circle, that's equal to 2 units. Here we can implement rule 11. I'll repeat quickly on rule 11. According to rule 11, if chord AB intercepts the chord CD at point O, then the following equation will be true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. we can definitely implement all 11 in our drawing. Why? Because in our drawing we have code AQ that intersects with code CP at point D. Again, code AQ intersects with code CP at point D. Repeat again, in our drawing we have code AQ intersects with code CP at point D. Therefore, according to rule 11, the following equation will be true: that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. Repeat again, according to rule 11, AD times DQ equals to CD times DP. AD is 1, DQ is 3, CD is the missing side, so it is as it is, and DP is equal to 5. 1 times 3 is 3, so 3 equals to 4 to 5 times CD. We divided this equation by square root of 5 and finally found out that CD equals to 3 over square root of 5 units in length. This is the missing side CD that is equal to 3 over square root of 5 in its length. In the next step, I copy this right blue-green triangle, this right green triangle CDB in a new page, and implemented the Pythagoras theorem in this right green triangle CDB in order to find out the missing side CB. So actually, this is the right main triangle DCB. So we are looking for there on this triangle DCB. According to the Pythagoras theorem, in the right triangle DCB, dB square equals to DC square plus CB square. Again, dB square equals to DC square plus CB square. dB is equal to 5, therefore dB square is equal to 5 squared, that is 5. And this equals to DC square. DC is 3 over square root of 5, therefore DC square is 3 over square root of 5 squared. Plus CB square. CB is the missing side, so we leave it as it is. In the next step, we subtracted the 3 over square root of 5 square. Actually, 3 over square root of 5 square equals to 3 squared, that is 9, over square root of 5 squared, that is 5. So in total, 3 over square root of 5 squared equals to 9/5. And here we have plus CB square. Here we subtracted 9/5 from this equation, and finally found out that 5 minus 9/5 equals to CB square. Here we multiplied 5 by 5 and then we divided by 5 in order to overcome a factor with 9 over 5. So 5 times 5 is 25. So in total, in the numerator of this expression we have 25 minus 9 divided by 5 equals to CB square. 25 minus 9 is 16. So in total, this expression equals to 16 over 5. That is equals to CB square. We took out all of this equation and finally found out that CB equals to the square root of 16, that is 4 over square root of 5. So in total, CB equals to 4 over square root of 5. Here, the missing side here, CB equals to 4 over square root of 5 units in its length. Our mission is to find out the area of this green shape. The green shape it is actually the right green triangle, triangle DCB. So our mission is to find out the area of the green right triangle DCB. We know that the area of any triangle, equals to the base of the triangle times the height of the base over 2. We choose the base as DC, and the height must be equal to CB. The height must be CB because it's 90 degrees with the base DC. Repeat again. The base is DC, the height is CB divided by 2. DC is 3 over square root of 5. BC is 4 over square root of 5 divided by 2. So they are of the green shape because to the value of this expression. The value of this expression is equal to 3 over 4 is 12, and square root of 5 times square root of 5 is 5, divided by 2. 12 over 5 over 2 is 12 over 5 times 2. So it is 12, and 5 times 2 is 10. So there are the green shape equals to 12 over 10 square units. We divided both the numerator and the denominator of this number by 2, and found out actually that 12 over 2 is 6, and 10 over 2 is 5. So in total, actually found out that area of this ring shape equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this ring shape according to the second method. We know that AOB is a quarter circle, therefore angle AOB equals to 90 degrees in its size. In addition, we know that AO equals to OB, they are both the radii of the quarter circle, therefore they are equal to each other. But the radius OB equals to 2, therefore the radius AO must be also equal to 2. We already found out that AD equals to 1 and DO equals to 1 in the first method. And then we did a construction, that is to say we completed this quarter circle to a circle, and we extended the radius BO by straight line until it touches the circle at point P. When you extend a straight line by straight line, the result is a straight line, so BP is a straight line, and according to rule 3, the sum of the angles on the upper side of BO at point O must be equal to 180 degrees, therefore the missing angle must be equal to 90 degrees in its size. I repeat again that BP is a straight line, but it is a straight line that touches the circle at 2 points B and P, therefore BP is a chord, but BP is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore BP is the diameter of the circle, and PO is the radius of the circle, that is equal to 2. We extended side CD by straight line, and we already found out in the first method that the extended side CD must touch the circle at point P and not in any other point. Okay? And then we focused on the small right triangle DOP. We defined this angle as theta. We already found out that this angle equals to 90 degrees, so the missing third angle must be equal to 90 degrees minus theta. 1 equals 90 degrees minus theta plus theta equals to 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on the big right triangle PCB, and the big right triangle PCB, this angle equals to theta. This angle equals to 90 degrees, therefore the missing third angle here must be equal to 90 degrees minus theta. In the next step, we proved that the big right triangle PCB is similar to this small right triangle DOP. So why the big right triangle PCB is similar to the right small triangle PDO? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write out that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we found out that all the triangles inside the big right triangle PCB are correspondingly equal to all the triangles inside the small triangle PDO, therefore the big right triangle PCB is similar to the small right triangle PDO according to angle similarity rule. And from the fact that the big right triangle PCB is similar to the small right triangle PDO, we will derive that the following relationship exists between their sides. We will derive that side PD in the small triangle over side PB in the big triangle equals to side DO in the small triangle over side CB in the big triangle, and it is equals to side PO in the small triangle over side CP in the big triangle. PD is square root of 5, PB is 4, DO is 1, and CB is the missing side. Actually, DO is 1 and CB is the missing side. PO is 2, and here, what is the length of CP? CP in total equals to CD plus square root of 5. Again, CP equals to CD plus square root of 5. Again, here, CP equals to CD plus square root of 5. So, according to question 1, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over CD plus square root of 5. Those two expressions are equal to each other, therefore we get equation 1 from those two expressions that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation and equation 1 and found out that square root of 5 times CB equals to 4. We divided this equation 1 by square root of 5 and finally found out that CB equals to 4 over square root of 5. There is inside CB equals to 4 over square root of 5. We continue to focus on the long equation 1. According to this long equation 1, those two expressions are equal to each other. Therefore, we get equation 2 from those two expressions that are equal to each other. So, according to equation 2, we should found out that square root of 5 over 4 equals to 2 over CD plus square root of 5. Here, we cross multiply this equation and equation 2. We finally found out that according to this equation and equation 2, square root of 5 times CD plus square root of 5 equals to 4 times 2, that is 8. Here we open the brackets on this side of this equation and equation 2 and found out that square root of 5 times CD plus square root of 5 times square root of 5 is 5 equals to 8. Here we subtracted 5 from this equation, equation 2, and finally found out that square root of 5 times CD equals to 8 times 5, that is 3. Here we divided this equation 2 by square root of 5 and finally found out that CD equals to 3 over square root of 5 units instead. Let me see inside here, CD equals to 3 over square root of 5 units inside. Repeat again, our mission is to find out the area of this green shape. The green shape it is actually the right triangle DCB. So our mission is to find out the area of the green right triangle DCB. The area of any triangle equals to the base of the triangle times the height to the base over 2. We choose the base is CD, the height is CB, divided by 2. DC is 3 over square root of 5, CB is 4 over square root of 5, divided by 2. So the area of the green shape equals to the value of this expression. The value of this expression equals to 3 times 4 is 12, square root of 5 times square root of 5 is 5, divided by 2. 12 over 5 over 2 is 12 over 5 times 2, so it is 12, and 5 times 2 is 10. So it is 12 over 10. We divided this number, both the numerator and the denominator of this number by 2. 12 over 2 is 6, and 10 over 2 is 5. In conclusion, we found out that the area of this green shape equals to either 6/5 square units, or in terms of numbers, it is equals to 1.2 square units in itself. So in both methods, we found out that the area of this green shape equals to either 1.2 square units or 6/5 square units. Okay, thank you very much.